Hello, welcome back. Today we're going to have a lecture on basic information theory. I'm Professor Wu. So let's get started. All right, so what is information? If I tell you two different facts, first, tomorrow the Earth will still be going around the sun. Fact number one. Fact number two, tomorrow an asteroid will destroy the world. Now, notice that this sentence has more words than this one. Which sentence feels like it gives you more information? Okay. Hopefully, you will say that an asteroid will come and destroy the world. That sentence gives you more information, even though it has less words. So we define information in information theory based on uncertainty. So if we look at the first statement again, tomorrow the Earth is still going to be going around the sun, right? If you think about it, how certain are you that this will happen anyways? Well, you're probably going to say this is very, very likely, right? So you're highly certain. In fact, most people will say they are 100% sure that the Earth is still going to be going around the sun tomorrow, right? Therefore, events that are highly likely, something that you expected anyways, doesn't really tell us anything. Doesn't tell us anything. In contrast, in the second statement, where tomorrow an asteroid will come and destroy the world, well, this is highly, highly unlikely event, and is not what you'd be expecting. Therefore, this statement contains a lot more information. From these two observations, we conclude that information from this perspective has an inverse relationship to the likelihood of happening, right? The higher the probability, right, the lower the information. If we know it's going to happen anyways, then it's not giving us that much information. In contrast, if we didn't know it's going to happen, it's very unlikely event, then there's a lot more information. The concept of information is therefore related to the inverse of the probability equation. Specifically, is the log of the inverse. So information in information theory is defined as I is equal to the log of 1 over p. So inverse relationship. Now, let's look at the two statements in this equation with this equation. So tomorrow the Earth will still be going around the sun, right? So if we are basically 100% sure this is going to happen, the probability is 1. So in a probability sense, it's 1, but in a information sense, it really contains zero information. If we're 100% sure it's going to happen anyways, then we're not learning anything new. From information theory perspective, then I will have 1 divided by the probability of the event, which is 1, resulting log of 1, which gives us 0. Notice how now if the somebody telling us that Earth will still be going around the sun basically give us no information. You see how the log basically give us this result. Now, with the second statement, the asteroid tomorrow will destroy the world. Most of us will consider this probability to be very, very small. It may be even smaller than this. And from a probability sense, therefore, it contains an enormous amount of information, right? So if we plug this tiny number in and find the information, notice how it's much, much larger than 0. So I want you to take a second, pause the video, and let's try this. We have 3 basketball players that's playing a 3-way game. Kate is an expert player, very, very tall. So the probability that Kate is going to win is 95%. Matt is a bad player and not tall at all. Therefore, his probability is roughly 4.99%. And Alice, she can't walk and she's blind. So the chance of her winning is very, very small, 0.00001. Okay. How much information is contained in each statement? Okay. So I want you to pause the video now and try to find the information of each one of these statements. Okay. Hopefully you are able to see that you can calculate Kate, right? Let's look at this part, for example. Kate, if Kate wins, it doesn't really tell us that much information. However, if Matt won the game, something interesting happened. And if Alice won the game, something has gone wrong. So notice how when Alice won the game, it provided the most amount of information because it is also the least likely event. Now, I calculated three times to demonstrate that when you calculate information, it depends on the base value. The base value could be E, 2, 10, and this heavily depends on the context. Most of the time is either E or 10, E or 2. Okay. Now, the base value is a way of encoding information. You can think of it that way. What do I mean by that? Well, we can encode concept and numbers into numbers. So you can say the number two can be in base two, base three, or base 10. So the number two, notice how when you try to count in base two, which is binary, it would be 0, 1, 2, 3, 4. So every single time it reaches two, it essentially goes to the next digit, right? So that's how binary works. Now, if you do base three, then it'll be 0, 1, 2, 3, right? So it's only a 3 that it ticks over. Base 10 is goes all the way to 9, and then when you tick the next one to 10, it goes to 1, 0. So when we pick the base, we're basically picking how we want information to be represented. Do you want a binary? Do you want to be base 10? Right? Us humans, we're used to base 10, this type of counting, right? We're really used to this because, well, scientists believe it's because we have 10 fingers. But in reality, we could have used base 2 if we had 2 fingers, right? So, so when we work with computers, we tend to like base 2. Okay. All right. So why is using base 2 or base 10 better in certain situations? Let's say we are flipping a coin, 50-50 chance. Notice how if a head is flipped, how much information is gained. If we use base 2, it's saying that 1 bit. Now, 1 bit makes a lot of sense because 1 bit tells you one heads or tails, right? 1 bit of information is either 0 or 1. So for this particular case, when we use base 2, right, it's when basically you want to think of information in terms of bits. Okay. All right. So the key takeaway here is the more rare the event, the more information it conveys. Right. The presentation of information depending on the base. How do you want to store that information? Base 2, base E, base 10, right? And therefore, 1 log of 1 divided IP is the information. Okay, 1/p is really the raw information. Log is used to store it, giving us information is equal to log 1/p. All right. So understanding information leads us into this concept of entropy or chaos. Entropy. So, what is entropy? We've heard of that from physics, perhaps. So, now that we know the equation of an information, this is information that happened. Notice the past tense, something that happened. If it hasn't happened yet, then we can't calculate the information, right? So, if a specific event hasn't happened yet, then there's a lot of randomness and chaos. Then, how do we go about measuring this chaos? Well, the measurement is called entropy. We measure the chaos, the entropy, before events happen. Let's say that we have a three candidate running to be the mayor of Boston, and the individual probability of winning for candidate one is 10%, 40%, 50%. 1, 2, 3. For using information theory, we can measure the information if an individual has won. So if we know candidate one, we know how to calculate the information, right? But before the election takes place, you can only measure the uncertainty of the election. You can't measure any information. And this measurement of uncertainty or chaos of random events that hasn't happened yet is called entropy. Okay? So, so how do we go about measuring entropy? Well, let's say, use this example. Let's say your life after graduation can go turn out four ways. So these are the four ways. Found a job you like, found a job you didn't like, moved back home with your parents, you won the lottery. So these are the possible, I mean, there's more than four, but pretend there's only four possible outcomes. So it hasn't happened yet because you haven't graduated yet, but we can measure the total chaos that you will experience in your life, which is entropy. And the way we do it is that we simply calculate the event of every possible event, just calculate the information of every possible event. So for the first one, we know how to calculate the information there, which is 1 over the probability, right? 0.7. Then the second one is 1 over the probability again. So third one, log of 1. So we basically can calculate the information if if each individual event happened. Right? So we know all the probability of events happening. And we know the information. Right? It hasn't happened yet, but we know the information for all possible outcomes. Right? Entropy to measure the entropy or the chaos out of these four possible outcomes. All we have to do is find the average information using the expectation formula. Now remember, the expectation of x is the integral of x px, right? Dx. Therefore, the expectation of information is equal to the average information px dx. So we know all the information already. We simply have to follow the equation where we have information pxi. Okay. Therefore, the equation is right here. The average information before things happen will be the information for the first event, which is right here, times the probability of the first event. Information of the second event times the probability of the second event, so on and so forth. So this right here is how you essentially calculate entropy. How do you measure chaos before things happen? You find the average information, right, before it happened. With in entropy, you can either do a continuous domain or a discrete domain. Okay? Sorry, I said it backwards. Discrete domain or continuous domain. All right, continuous, then you have to find the integral. Over here is a cold example where if we want to calculate the entropy, right, you simply take the log of p times p, assuming there's a minus. So this is a code on how you can calculate entropy for discrete events. Right, let's try this yourself. Okay, suppose you have a box containing 5 different colored balls, 2 red ball, 1 blue ball, and 1 green ball, right, and 1 yellow ball. So therefore, what is the entropy of the ball distribution for the box? Okay, pause the video. You want to do this? I think the answer is on the next page. Yep, over here. Hopefully you were able to get this. And we over here use base. I think we use base E. Yeah, use base E. Okay, so here's the solution. Hopefully you're able to get that. I actually typed this into ChatGPT, um, like 2023. So 2023, a couple of years ago. Maybe ChatGPT by now is better. But when I typed it in, ChatGPT got it wrong. So it's funny. Anyways, now that we've done some entropy with discrete domain, let's practice calculating entropy for the continuous. Okay, so pause the video, make sure you can do this, and you can check your solution here. An interesting fact about entropy, equal probabilities always yields the largest entropy, right? So over here, I roll the code. Basically, I keep generating random probabilities. And then I add that random probability if the entropy is higher. So this means that I keep generating random probabilities. There, notice how the entropy is getting higher and higher. I only print it out when it gets higher. And it's the highest when all the probabilities are the same. right? This is a general observation that when the probability are the same, this is when entropy is the largest. Largest. This is a rule about entropy. Right. Now, when you want to just measure, if you want the value of entropy, you can calculate it. But if I tell you entropy of a system is zero point 0.9, it's not very helpful because you don't know if zero point 0.9 is a small or a large number, right? Depending on the event, zero point 0.9 could be either very large or very small. Therefore, sometimes it's useful to scale the entropy between a value between 0 and 1 in the case where 0 will be minimum entropy and 1 will be maximum. So if you scale your entropy between this, it's much easier to use to communicate. And we call this version of entropy normalized entropy, right? So if you want to calculate normalized entropy, you simply calculate the entropy, which we just learned how to do. And then you figure out the maximum entropy. The maximum entropy is from the last slide. It's when all the probabilities are the same. You can essentially just put that in and you calculate the maximum, and then you will figure out a ratio. This ratio scales entropy between 0 to 1. Okay, so that will be an easier way to communicate this magnitude of entropy. Right, so the concept of entropy is quite helpful. Understanding entropy leads us to measure relationship between distributions. Okay, so once we understand, have seen the equation for entropy, which is the average information, right? It leads us to this concept of cross entropy, KL divergence, mutual information, right? There are a lot more, but these are the ones we're going to cover. Specifically, let's now cover the concept of cross entropy. Now, remember, entropy is the average information, right? So it's entropy is the integral of the information times p of x dx. Right? So this is what entropy is, which I think entropy is denoted by H. That's right, H. So we denote entropy by H. So that's what entropy is. Now, um, which I'm going to rewrite this. Entropy is equal to the integral of p of x log 1 over p of x dx. Okay, so this part is information. This is information. So the average information of p of x using p of x as the probability. Cross entropy between P and Q is different. Is the average information of Q using P as the probability. So notice this. Here's the average information of Q using P as the probability. Okay? So this cross entropy, what it does is you put two distributions in, P of x and Q of x, and it measures the difference between them. If the number difference between them is large, then it's a large number. If the difference between them is small, then it's a small number. Let's look at a quick example. Over here, we have an example of two distributions, P and Q. Now, these P and Q are quite different, right? This is the example that they're different, where they have zero point 0.1 for P and 0.7 for Q. And over here is 0.9, 0.3. So the difference is pretty large. And therefore, you would expect that the difference, as measured by cross entropy, is some larger number. However, now let's look at these two distributions, 0.1, 0.2. Now, 0.9, 0.8. Now, these two distributions are much, much more similar, right? So, and the cross entropy between them should also show a small difference. So, cross entropy is a way of measuring the difference and distance between two distributions. The larger the cross entropy, the more different they are. And the smaller the cross entropy, then the smaller the difference, the more similar the two distributions are. Now, cross entropy, this equation, is a very, very important equation. We previously learned the mean square error, which looks like this. And mean square error, like I told you, is one of the most used machine learning equation in machine learning. And the second most is actually the cross entropy, right? So this cross entropy right here, cross entropy. The second most used, therefore, it's very important equation that you will need to know. Now, with cross entropy, remember from our sampling class that you can essentially approximate the cross entropy by generating samples from P of X, and then approximate the result. So you can calculate cross entropy and approximate the result this way as well. Now, cross entropy, let's look at three different kinds. The first is quite different, and as I showed you previously, that the distance between them is larger. And when you make a difference smaller, the distance is also smaller. However, you would expect that when their two distributions are identical, that's when it's minimal. And when it's identical, then previously we have P of Q, right? So this is the cross entropy, which is equal to the summation of P of X log of 1 over Q of X. So that's cross entropy. Now, what happens when P and Q are identical? P of X log of 1 over P of X. So this right here is identical to just entropy itself. So when two distributions are identical, the cross entropy reduces down to just entropy. Okay. Right. Notice how if P is equal to Q, then it's just PP here. So the distance between P and Q is measured via cross entropy, and when they are identical, then cross entropy reduces down to just entropy. Okay. So as the two distributions P and Q become similar, right, their difference gets smaller. And when P and Q become equal, cross entropy reduces down to regular entropy. Therefore, you can picture cross entropy as always larger than entropy. Moreover, cross entropy is the total entropy adding Q. So you can think of entropy as like this chaos, right? And then you start off with P of X. Therefore, there's some kind of chaos, right? But if you then add Q of X, you are increasing the chaos by the amount, the entropy from Q. So, and therefore, cross entropy is basically the additional entropy that you add to the original entropy due to P, right? So if you want to measure the additional entropy, you simply take the cross entropy and subtract the original entropy, right? So once again, and the difference between them is the additional entropy because of Q, additional chaos. Whenever you add an extra distribution, you're adding more chaos into the system. And to measure that additional chaos, you simply take the cross entropy and minus the original entropy. And this excessive entropy is called the KL divergence. Okay? So KL divergence is basically a second way to measure the difference between two distributions. So, like I said, you can imagine cross entropy as the additional. So you start with some entropy. After you introduce Q, you have the whole system has more entropy, right? So therefore, you take the entropy after, subtract it from before, that gives you the additional entropy, which is called KL divergence. KL divergence. Now, KL divergence is commonly written this way, where you have P Q. Like cross entropy, we write it this way, HPQ. But KL divergence, you write P with this parallel line Q. Now, KL divergence is the excessive entropy due to the introduction of Q. However, normally in Wikipedia, you see the equation this way. So you start from the difference. After a bunch of mathematical manipulation, you will get this. So this right here is the definition of cross entropy. Okay. Okay, now that we understand cross entropy, the next concept we're covering is mutual information. Mutual information in information theory is a way of measuring the dependence between two distributions. Now, remember I told you about dependence, right? The dependence, whenever we have a joint distribution, we can rewrite the joint distribution as p of x given y times p of y. However, if x and y are independent, there's nothing to do with each other. Therefore, p of x y is equal to p of x times p of y. Now, mutual information is the KL divergence between p of xy and p of x, p of y. What happens if they are the same? So if p of x y is equal to p of x p of y. If they're the same, this is the definition of independence. Of independence. Right? So if they're the same. However, if p of x y is very different from p of x p of y, then that means they're dependent. Therefore, if you measure the distance, the difference between p of x, p of y, you can measure how dependent two distributions are. So if you simply take the KL divergence, which you measure the difference between p of x times p of y, which by definition KL divergence is p of x y, p of x y divided by this. So we just did KL divergence, and now we basically found the KL divergence between these two distributions. And that is defined as mutual information. Okay. Right. Let's pause the video. You can go back to the slides and then kind of study these definitions, but take this as the probability table and see if you can calculate all these things. Right. This takes practice to sink in. Okay. Pause the video. Go through this. All right, so I provided a solution here, so you can essentially study them. All right, finally, let's practice calculating KL divergence. So previously, we calculate them in discrete terms. Now we're going to calculate them in continuous terms. Let's load this file. Notice that the distribution between male and female distribution looks similar to each other while the dating profile. So this implies that if you find a, like, notice how these two are similar, right? That's all that's saying. So if they're similar, this implies that if you find a distance between marriage distribution, they should be this very similar. However, if you find a distance between these two, that should be farther. Okay, so you want to use KDE to identify the two marriage distributions. So you want to identify the distributions, and then as well as the male dating distribution, which is right here. So you identify these three, and then the distance between the two of them should be much shorter than the distance between the two of them. Okay, so make sure you can do this question. Okay, and I think that's it. That's the end of today. I will see you in the next lecture.